Hello and welcome back to this episode of The Game of Drones. I'm Hal Cowan and today I'm joined by Charlie Stevenson, who's going to be talking us through how drones are detected and counted using real-world physics. Over to you, Charlie.
Thanks, Hal. With drones being surprisingly cheap, effective and increasingly autonomous, it's becoming increasingly important that we understand how to stop them. A device that costs a few £100 can surveil, disrupt or even attack targets worth millions. One of the first steps of doing so, regardless of method, is knowing where the drone is and where it's going. There are many different detection methods, each with its own pros and cons. The three main ones we will discuss today are RF detection, radar and IR detection. The first method of detection we will discuss is RF detection, meaning radio frequency detection. The simplest way to detect a drone is by listening to its noise. This can be done acoustically by listening to its sound or electronically using RF detection, which picks up electromagnetic signals such as control links or video feeds. These are often in known frequency bands. RF detection works by monitoring these frequency bands and observing for any given signals. With multiple antennas at different positions, you can compare the phase difference between signals received and triangulate the direction of the emitter. However, this method has serious limitations. Fibre optic drones do not emit their electromagnetic waves into the atmosphere, they are confined within the waveguide, which is the cable. Furthermore, in signal-dense environments like urban areas or active battlefields, it can struggle due to the level of background noise hiding the desired signals. The next method of detection we will discuss is radar. Radar operates by emitting electromagnetic pulses and measuring the reflection. The distance of the drone can be calculated from the pulse's velocity, the speed of light, multiplied by the time taken for the pulse to return, and finally divided by 2 as it is a two-way journey. Radar also measures using the Doppler effect. A moving drone can cause a phase shift proportional to its velocity and inversely proportional to its wavelength. This allows the radar's computer system to filter out stationary objects like buildings and terrains. Furthermore, different models of drones can have different speeds of rotation of blades, which can help further clarify if the signal is a drone and sometimes what model it is. This is called microdoppler. One limitation is that small drones have very low radar cross-sections, often comparable to birds. Detecting them reliably requires higher frequencies, better signal processing and more complex systems. Finally, we will discuss infrared detection. Drones contain motors, batteries and powered electronics, none of which are perfectly efficient. These release waste heat, making drones thermally stand out from their surroundings. Thermal emission scales with respect to temperature, as described by the Stefan-Boltzmann law, where the total amount of energy emitted by a body is proportional to the fourth power of its temperature. While this law applies to ideal black bodies, it still shows an important trend. As temperature increases, objects emit more infrared radiation. Military systems often operate in two bands. MWIR, known as mid-wave infrared, which is 3 to 5 micrometers, and LWIR, known as long-wave infrared, which is 8 to 14 micrometers. Objects at 300 to 500 Kelvin emit strongly in these regions with little atmospheric interference, which is around the temperature of normal machinery like drones. Finally, classification can be made through infrared profiles of drones once the size of the drone is known. This can then be used to determine the distance the drone is from the receiver. Overall, this method is very useful, but it can be limited by the environment too. For example, background infrared from the environment and the sun can confuse the detectors. Once a drone's position and trajectory are known, kinetic interceptors can be used to physically destroy it. While effective, these systems are expensive, limited in ammunition, and often very unsuitable for urban environments. You would not want to take down a full building in an attempt to destroy a drone. Because of these limitations, modern counter-drone systems often prefer non-kinetic methods, either by denying a drone control, such as by jamming, or destroying it without physical projectiles, like using a laser. The first of these is by jamming. Drones rely on electromagnetic waves for guidance, for which the frequency bands are often known. The idea of jamming is simple. You transmit a much stronger, noisy signal on the same frequency as the drone, which superposes with the original useful signal, making it harder to decode for the receiver. This is mainly effective due to the geometric spreading of GPS waves. These are used to control the drones and they tend to be very weak and have a low power by the time they reach the drone. This can be exploited by sending high-power electromagnetic signals to the drone to confuse it. The receiver's ability to decode the signal from this is given by its signal-to-noise ratio. If you increase this noise by sending a wave the same frequency of the signal, this reduces the signal-to-noise ratio, eventually resulting in the receiver not being able to decode the signal, resulting in control of the drone being lost. This can be done using the environment too. Things like fog increase attenuation of electromagnetic waves, significantly decreasing the power. Lasers are high-power, highly localized beams of light. The idea behind using lasers as a counter-drone system is that they can rapidly transfer energy into the material they strike. This process is known as laser heating, and at high intensities it can lead to laser ablation, where material on the surface begins to melt, vaporize, or break down. As this energy is absorbed, the drone heats up. If the temperature rises high enough, several failures are possible. Electronic components can overheat, motors can seize, and structural materials can weaken or melt. However, this process is not easy. As soon as the laser deposits energy into the drone, that energy also begins to spread out through the material via conduction, and it further dissipates into the surrounding environment. This means the laser must deliver energy faster than physics can remove it. If the beam isn't intense enough, the heat will simply spread away and the drone will survive. There are also significant real-world limitations. Lasers require a clear line of sight of the drone and must remain precisely focused on a small point of a fast-moving target. Atmospheric effects such as scattering, turbulence, dust, and humidity can all reduce the amount of energy that actually reach the drone through attenuation, increasing the time needed to deliver the required energy to damage the drone. This requires incredibly high power lasers, typically rated from 10 kilowatts up to 100 kilowatts or even more. This is the equivalent to dozens of kettles worth of power, all focused on one spot only a few centimeters wide. As a result, modern research into anti-drone laser systems focuses on not just the laser itself, but on beam control, power delivery, and energy storage. Ultimately, countering drones isn't about a single weapon or technology, but about understanding the physics of detection, information, and energy, and using them together effectively. From my perspective, what's most surprising about counter-drone systems is that none of them rely on a single piece of technology, but instead a combination of systems and physics across different fields.
Thank you, Charlie. In the next episode, we'll look at how drones adapt to these countermeasurements, a counter to the counter, you could say, and the uses of drones in current conflicts. That's all for today. Thanks for listening.